So our last two problems that we'll work through for Chapter 3 deal with doing solution stoichiometry. And what I want to make sure to highlight to you guys is that these problems are going to be very similar to two problems that we've already done. Sample problem 1316 dealt with calculating quantities of reactants and products in a chemical reaction. This was our roasting of our copper 1 sulfide. We basically had to write formulas, make a balanced equation, and then do unit conversions to walk between kind of masses of materials. Okay, so we'll kind of bring this problem back in a minute. And then our last problem that we'll work through deals with limiting reactant problems, but in a solution sense. Well, we already did a limiting reactant problem in problem 3.20, but again, it was dealing with masses. So what I hope you'll see is that there's not really too much that's different with our last two problems, other than rather than using a molar mass to walk between quantities in terms of grams to moles, we're going to use a molarity to walk between quantities in terms of a volume to moles. Okay, so here's problem 1326. We have a 0.1 molar HCl solution, and we're using that to simulate the acid concentration of the stomach. So we'd like to know how many liters of stomach acid will react with an acid tablet that contains 0.1 grams of magnesium hydroxide. So again, we need to treat this problem like we've done before. So again, I'm going to put a little note here that see problem 13.16. This is the same kind of problem, but with masses. Okay, but what we're going to need to do is we're going to have formulas that we need to get from our chemical names. We need to make those into a balanced chemical equation, and then we're ready to do our stoichiometry. Okay, so we need to write formulas down. They tell us an HCl solution, but magnesium hydroxide. Well, we know that magnesium is 2+, hydroxide is O-, so that means we have MgOH2. Okay. Putting this into an equation that we'll need to go ahead and balance. We've got MgOH2. We're going to react that with HCl. We're going to give that aqueous. And we'll learn more about this in our next chapter, Chapter 4. This is an acid-base reaction. Okay, but what happens is we make H2O and then MgCl2, and that's going to be, as we'll see in our next chapter, a soluble salt. Magnesiums are balanced here. My chlorine is not, so I'm going to put a 2 there, and that coincidentally happens to help with balancing the rest of our equation here once I put a 2 there for water. So magnesiums are balanced, chlorines are balanced, 2 hydrogens there, but we've got 2 more that are there, 2 oxygens, 2 oxygens. So we have our balanced chemical equation, and in this case, we know that we have 0.1 grams of our magnesium hydroxide, and we'd like to know how many liters of stomach acid we'll need to react with that. So I'm going to make myself a road map, not unlike the road map that we drew for this. So again, this is problem 316. They told us that we wanted to make this much of our copper oxide, so we used a molecular weight, a molar mass, to get to moles of this material, our balanced chemical equation to get to moles of oxygen, and then in this case we used a molecular weight again to go back to the grams of oxygen that would react to make that amount of solution. So in this case, we're kind of looking at it in terms of 2 reactants. How much of this reactant would we need to fully react with this magnesium hydroxide? We can again use our molar mass to get to the moles of MgOH2. We can use our balanced chemical equation to change who we're talking about and get moles of HCl. So the only place that this problem is different from problem 3.16 is right here in terms of how we walk from moles of HCl to liters. And that's where we use the molarity of the solution, which is equal to the number of moles of HCl per liter of solution. And again, that's something that they provide for us. They tell us that it's 0.10 molar. So they give us the unit conversion to walk to the quantity that we need. So now all that we have left to do is execute our road plan. So we've got 0.1 grams of magnesium hydroxide. And again, we're going to multiply that by our molar mass, which is 58.33 grams of magnesium hydroxide for every 1 mole of magnesium hydroxide. Again, this we get from our molar mass. We can change who we're talking about by using a balanced chemical equation. So 1 mole of magnesium hydroxide will react with 2 moles of HCl. So again, we get this from our balanced chemical equation. And lastly, the part that's new is we can use our molarity to convert 0.1 moles of HCl is in every 1 liter. So this is, again, a molarity. And note that this is the information that is new. Okay? And molarity is equal to 0.10 moles of HCl per 1 liter, or molarity is equal to 1 liter over 0.10 moles of HCl, right? If these things are kind of equal to one another, we can use them in either way. So that's why we could flip this, and we needed to, because if we go through and we look at our units, grams of magnesium hydroxide cancel, moles of magnesium hydroxide cancel. The only way to have moles cancel is if we have the mole part be on the bottom, and the mole part is what goes with the value of molarity. So the 0.1 goes there. Work out your math here, and again, if we look at significant figures that we have, we're going to have 2 significant figures in our answer. There's 2 that are there and 2 that are here. So we've got 0.034 liters of HCl, which equates to 34 milliliters of stomach acid. Put your logic hat on there. That kind of makes sense, right? 34 milliliters, that's about as much as you could probably realistically fit in your stomach. We're not going to fit 340 milliliters easily, and similarly, something smaller than that would seem pretty small. So use your logic hat and ask yourself if your answers make sense.